Good morning, everyone. Welcome to the MIPI Sensor Solutions for Autonomous Driving presentation. We'll explore and discuss how the highly configurable CSI-2 controller with the PHY subsystems can be tailored to address the various needs of autonomous driving, including examples and use cases applications. Our presenters include Joe Rodriguez, Product Marketing Manager from Rambus, and Justin Endo, Sales Marketing Manager from Mixel. So, Joe and Justin.
Yeah, great.
Great, thank you. Greetings, everyone. I'm Joe. Welcome to our presentation. So this presentation, as mentioned, is focused on providing insight into how sensors are being deployed in the autonomous driving market. The sensors deployed in the market are bound by the physics involved in vision. An engineer's challenge is to leverage the physics when innovating solutions to meet sensor requirements. The MIPI standard is a well-stocked toolbox we will all use to assemble solutions. In the introduction section, I will cover common requirements in the automotive sensor market. In the sensor section, we will both talk about why the MIPI standard is the cornerstone of the data acquisition systems being created. CND-PHY and CSI-2 controller-based sensors that meet a broad spectrum of requirements. We'll share customer examples. Essentially, you'll learn about the topics we discuss with our clients every day. We'll also discuss safety. Safety is the what IP and system providers like you must do to engage in this market. This includes a brief overview of the safety features you should consider when implementing your automobile system. Okay, I think I went too far. There we go. So the auto industry is in full transition. More and more auto manufacturers have pivoted their platforms to engage this market. For example, Hyundai is now targeting all new development with their new EV platform. Part of this transition to EV includes more and more sensor platforms. The forces driving the transition continue to provide value. What are these forces? Well, some of them are, of course, the MIPI CSI-2 standard, a consensus on what safety is, and the move to full EV platforms enables new compelling events. Another example of the forces involved is a long-term investment in materials science. These investments have reaped many, many benefits: lighter chassis, stronger materials, longer lasting batteries, faster charging. These all make the EV platform much more appealing, as well as the sensor market. In addition, the fact that ADAS requires more than one sensor for a trained AI network to be successful, this additional requirement has expanded the sensor market quite significantly. ADAS is complex. It was said 10 years ago, and it's still true today. To automate, you need a wide variety of sensors because everything a car contacts has a unique way it responds to the electromagnetic spectrum. Each frequency in the EM spectrum has specific characteristics: lower frequency, lower energy, lower resolution. A sensor to identify large objects is very different than a sensor that needs to identify a bicycle or a motorcycle rider. When creating a sensor to control the chassis, lidar may be the perfect solution. It has very specific bandwidth and data streaming requirements. Today, lidar sensors even span multiple frequencies in the spectrum in order to achieve their desired goals for ADAS. A backup camera in the visible space will impose different sensor requirements. Within the sensor market, there are many, many product opportunities. Add other factors including power, manufacturing costs to the equation, and you will see why MIPI CSI-2 is so valuable. So architectures, as mentioned, need to be balance many requirements to succeed to adapt to the electromagnetic spectrum. And each of these parts of the spectrum impacts the MIPI architecture. A mission-critical high-bandwidth sensor with continuous streaming requirements has specific techniques. Low power is usually a concern, but not the highest when balancing the requirements for a mission-critical sensor. This brings us to one of the key benefits of the MIPI CSI-2 specification. It allows system providers and architects to balance the requirements and innovate. It's that kind of flexibility. And innovation is not only interesting to the sensor development community, but it's how us IP providers are able to deploy high quality, reusable IP for so many different types of sensors with basically off-the-shelf components, just different features enabled for the different trade-offs or requirements you have. So now let's get into some of the details and provide some architectural examples of sensors. As we mentioned, the MIPI CSI-2 specification is really incredible in its flexibility, and it did change the mobile phone industry, and it has not changed. It's been adding features ever since then. In fact, it has leaned into the automotive market with new features that are being rapidly adopted in this market. Wisely, the new versions of the standard continue to be backward compatible. The benefit of being backward compatible and the continual buildup of valuable features allow IP providers to rapidly deliver high-quality IP, as mentioned, with the least amount of re-engineering. High-quality IP is what you should require from your MIPI IP provider. Furthermore, this backward compatibility enables system providers to have the benefit of being able to deploy modern systems that can plug in with components that are from a previous generation of the spec. They may not have all the whizzy new features, but the ability for them to actually work and provide value is really significant. Another reason why MIPI CSI-2 is a workhorse is flexibility. You can deploy 1-lane D-PHY, 4-lane C-PHY, or both in the same IP. You can support expanded virtual channels or not. You can add smart regions of interest or not, the specific feature inside the spec in the table above. A specification that allows you flexibility to balance your CSI-2 controller requirements and create a successful sensor should not be underestimated. So that'll be my part of this introduction and sensor section. I'm going to turn it over to Justin here in 1 second.
Great.
So,
yeah, thanks, Joe.
Sure.
So before we go more into about MIPI PHY in automotive applications, I thought we could do a similar overview of the history of D-PHY and C-PHY. So D-PHY has been around for quite a few more years. As you may know, it was first adopted back in 2009 by the board, while C-PHY is more recent, being approved in 2014. But both really have been the foundation of low power architecture and mobile adjacent applications since their debut. And over the years, we've seen significant increases in supported speeds, with D-PHY starting out at 1 gigabits per second per lane, and over time adding speeds up to 4.5 gigabits per second per lane in version 2.0, with 9 gigabits per second per lane supported by version 3.0 of the standard. MIPI C-PHY supports up to 6 gigasymbols per second per trio, which is an equivalent data rate of 13.68 gigabits per second per lane or trio, with a aggregate data rate of 41 gigs with 3 trios. And as of today, the next generation, version 3.0, plans on a lower symbol rate but a higher bits per symbol, an equivalent bandwidth of 20 gigabits per second per lane. In addition to pushing the bandwidth for each successive generation of the spec, both D-PHY and C-PHY have introduced new features over the years. Some examples include D-PHY power saving features, such as high-speed TX half swing and high-speed RX unterminated mode. Both were introduced in version 2.0 of the spec. C-PHY introduced similar features in version 1.2, namely low voltage high-speed TX and high-speed RX unterminated mode to save power. Both D-PHY and C-PHY introduced ALP and fast bus turnaround, and this was targeted for IoT applications requiring long channel and reducing the number of wires. D-PHY introduced this in version 2.5 of the spec, and C-PHY introduced ALP in version 1.2 and fast bus turnaround in version 2.0. So it really shouldn't be a surprise then that applications beyond mobile look to MIPI specifications to save on power. So looking more closely at D-PHY and C-PHY in automotive applications, D-PHY has traditionally been used when CSI-2 is needed for automotive sensors and cameras. And in the market today, there are multiple generations of automotive sensors and cameras used in applications such as that Joe mentioned earlier, and actually Grigor's presentation earlier today as well. And most of these are using a CSI-2 based D-PHY. My slides are jumping around a little. So when CFI was introduced in 2014, it initially gained traction for consumer applications. However, in recent years, we have seen an increased use of CFI for automotive applications, primarily with CSI-2, although some DSI applications as well. And in general, we have seen an increased use of MIPI for mission-critical applications versus strictly infotainment. So with the increase in CSI-2 based MIPI being used for automotive sensors and cameras, is it strictly a power reduction requirement that is driving this demand for MIPI, or is there more to this story? Well, another aspect to consider is the testability and reliability of the PHY. So for automotive applications, testability is of the utmost importance. And MIPI does have testability built into the specification. The universal configuration, for example, is the superset configuration with both transmit and receive functionality, and this supports full speed production testing. However, this does come with an area penalty, and Mixel developed a proprietary configuration we call TX Plus and RX Plus, which was originally based on an automotive customer's requirement. And this supports the full speed production testing of the universal configuration without the full area penalty, and also supports in-system full speed testability. And you can see a block diagram on the right that shows how a CFI-DFI combo TX Plus configuration could be implemented. This includes the high-speed TX and a simplified high-speed RX to support the full speed loopback. Now, when designing the IP itself, if it will be used for mission-critical applications, we need to consider the mission profile. This often requires designing for a high sigma yield design requirement, such as a target CPK of 1.67 or even up to 2, and also requires designing for a higher junction temperature. There's also an automotive version of the PDK from the foundry that is required. There is additional testing and verification that goes along when designing an automotive IP. Stress testing, such as voltage stress, with the ability to screen out latent defects in the system during testing is important, along with other testing such as H-toll to ensure the lifetime requirement. There are also reliability simulations that are run for aging and EMIR. So with that, I'll hand it back to Joe to highlight a few sensor subsystems for automotive use cases, to highlight how a MIPI and controller can work together to meet different requirements at a system level. So Joe.
So here we have an automotive sensor subsystem architecture. In this case, it's an aggregator. And in this, you can have a configuration where it supports 1 or 2 sensors. And it's configurable by software or at power up, however your solution space organizes your system. And you can have like one high lane rate sensor or a mid-range sensor that splits the resources here. So this is a really common automotive subsystem architecture, and I'll show you a little bit of the actual implementation details here on the next slide. So in this case, you'll see the same aggregator that was on the previous side. On the left here, you see the lower bandwidth sensor with 2 lanes of DFI and 2 lanes of Trio replicated twice. So the sensors are there on the top left. And on the right side is the more high bandwidth sensor with 4 lanes of DFI and 3 lanes of Trio. Now, this can be implemented with in what we call bifurcation. And you can do, in this diagram, since Mixel and Rambus both support this bifurcation, we can do CFI and DFI, or CFI alone or DFI alone. That kind of depends on what market you're trying to fit into. In this case, there's 2 instances of the controller and 2 instances of the PHY, with 1 clock lane for each instance. So the other thing that has to be supported on the from the sensor or from the PHY and controller side is that when you're in the 4-lane, 3-lane configuration on the top right, that second PHY that's still on the silicon has to be support, having a clock disabled when you configure the system. So this is really valuable for a lot of people. They have one IC that can fulfill multiple roles in the market, or within a flexible subsystem that they deliver in this market. Either way, it can be separate or all in one bit of hardware. So one of the other things that we do very commonly is implement a FIFO. A lot of systems have their own FIFO, but what I'm talking about here is valid for your FIFO or a FIFO that comes off the shelf from whatever MIPI IP provider that you choose. In this case, the main purpose is to handle basically bandwidth matching. Is the sensor data coming in a little bit too rapidly for the system to digest? Can your sensor allow breaks in the streaming of it, or does it have to be continuous? Excuse me. And the idea here is that you define the low and high end ranges of your system, and you'll be able to best apply the size of FIFO that you need. And in this case, you want to be able to do both the data types, the virtual channels, whatever, whether you're using extended or not, and the number of pixels. So you have to basically have control for all these things in whatever IP you end up deploying. So here's an example of bandwidth matching, where the graphics don't seem to be coming up on my version, but on the left side, the sensor here is essentially running at half the clock rate of the PHY. In this case, it's the 2.5 gigabit per second per lane DPHY. So that's the clock rate there, the 312 megahertz, and then the system clock from the sensor is running at half that rate. So basically, with this FIFO, you have to have a fairly significant or a fairly light or fairly significant FIFO to handle this bandwidth matching. So that's the idea behind this this example. So that's a brief overview of some of the architectures that are being deployed in the automotive market. We'll get into more examples, and I'll turn this over to Justin for the next section on safety.
Yeah, thanks, Joe. So before we kind of get into more about safety, we've covered a lot so far about sensors within the context of MIPI, but I thought it would be good to take a step back and look at the industry definition for autonomous driving. The most famous comes from the Society of Automotive Engineers, or SAE, which is defined driving automation levels from level 0 to level 5. So looking at the diagram, starting at the right, level 5 is considered full driving automation. And this is a system that can drive itself everywhere under all conditions with no default back to the person inside the car. And as far as I know today, no one's announced that they're targeting level 5, but let me know if you've heard of one in the Q&A or comments. Level 4 is considered high driving automation, and this level of automation is seen in the market today. Level 4 technology is employed right now by Waymo One, which is an autonomous taxi right now in East Phoenix. They're beta testing in downtown Phoenix and SF. There's also another taxi service by a GM subsidiary called Cruise in SF with plans for Austin and Phoenix, and a handful of other projects that are considered level 4, but notably, this is not available in consumer vehicles. These are, taxi services. Level 3 requires the driver to take over when the system encounters a problem. There are some consumer vehicles that support level 3 automation in the market today, but it's still not widespread. It's currently found in select Mercedes models in Germany called Drive Pilot, also in a small number of Honda Legend in Japan. And then we come to level 2, which is when we think about autonomous driving today, most features fall under SAE level 2 or partial driving automation, where the driver still monitors the driving at all time. Advanced driver assistance systems or ADAS systems in Tesla or other high-tech cars available to consumers today are typically classified as level 2. Now, my main takeaway here is that level 1 driver assistance and level 0 no driving automation features still require advanced sensors and cameras. And some of these features include collision warning, automatic emergency braking, blind spot warning, and lane departure warning. So with that in mind, let's discuss a little bit more about automotive functional safety. So ASIL, or the Automotive Safety Integrity Level, is a risk classification scheme defined by the ISO 26262 Functional Safety for Road Vehicles standard. ASIL ratings can go from quality management to ASIL A to ASIL D. ASIL C and ASIL D are considered high-level safety critical, and the rating is determined by this matrix here on the left, which is based on 3 key parameters: exposure, controllability, and severity. Exposure is the probability of the vehicle being in a risky situation that can cause damage to a person or property, and this goes from E1 to E4, with E4 being the highest probability. Controllability is the extent to which the driver can take control of the vehicle, and this goes from C1 to C3, with C3 being the most difficult to control. And severity is the seriousness or intensity of damage or consequences to people's lives. And this goes from S1 to S3, with S3 being life-threatening. So from this chart, you can see that an ASIL-D rating would be an E4, C3, S3, meaning high probability of being in a risky situation with high difficulty to control the vehicle in a life-threatening situation. Now on the right, you can see in the diagram some common automotive features with the commonly associated ASIL levels. So to bring it back down to the MIPI PHY and controller level, IP providers typically provide an automotive MIPI IP as a safety element out of context, or SEOOC. Essentially, as an IP provider, we don't have prior knowledge of the system into which our IP is going to be integrated. So in order to ensure proper integration of the IP, there is a specific deliverable defined by ISO 26262 called the safety manual. And this calls out the assumptions, such as the assumptions on safety functions, the assumptions of use, such as the target ASIL level and operating conditions of the PHY. It also highlights safety mechanisms, both internal and external, and it highlights the safety lifecycle of the IP. And this ensures that the IP is integrated properly and explicitly calls out the requirements to ensure that the IP meets the ISO 26262 standard. So in addition to the safety manual, there are a few hardware safety analyses that are defined and required by ISO 26262. These include the DFMEA, or Design Failure Mode and Effect Analysis, and the FMEDA, or Failure Modes, Effects, and Diagnostic Analysis. The DFMEA is used for systemic failure analysis, and the FMEDA is used to analyze hardware IP random faults. Both of these, in addition to the safety manual, are required if the IP will be ISO 26262 certified. In most instances, we have seen requests for the IP to target ASIL-B, with the SoC targeting ASIL-B or ASIL-D. So with that, I'll pass it back to Joe to discuss specific safety features that are built into the CSI-2 controller.
So let's get into a little more of the details about what you should expect to do when you deploy automobile safety. In this case, it's the things that we've recommended and implemented in our controllers. So every team will need to add fault detection logic. I mean, that's part of the DFMEDA and all the deliverables that Justin just outlined. So the next few slides we'll talk about, in this slide it's BIS, but I'll talk about some of the other examples that you need to implement. So we believe that built-in self-test of the controller is a really fundamental and valuable solution. It's focused on fault detection of the ECC, the CSRC, the parity mechanisms, and doing this all on power up. And then that way, you know, when you're powered up from the get-go, if you're not receiving an interrupt request or that has a failure, then everything's good to go and you can continue with your boot up sequence of the overall system. So you can develop built-in self-test to go really deep into the entire RTL. So in terms of the controller, for us, it's the best way to get control of the deliverables that are required in this market. Of course, it doesn't replace the SoC testing. It's simply a layer of the overall requirements that you're going to have to implement in your system. It's a really good starting point to know that at least your controller and PHY will be able to do these things for you. Another component of what we've implemented is the controller protection and safety watchdog. So data protection features are very important. I mean, that's the actual crown jewels there. And its coverage should be comprehensive. It should include pixel buffers, the protocol at all levels, and like a lot of the deployments in the industry right now, redundancy is a valuable tactic. So we've added some redundancy to add to the visibility challenges that everyone has when implementing auto safety. So you also need to track the order of the data. So you want to be able to flag if the data came in even if it's valid and it's not of order, you definitely need to be able to track that. That's a serious violation of integrity. So you need to include parity, CSRC, redundancy, order protection, and a watchdog timer to eliminate rogue operations and assure coverage. So having an idea of some of the things that we've done in the RTL hopefully is a very beneficial insight to how you're going to do the rest of your system. But it's not just important to identify them, but you have to implement a way to recover from them. So that's the idea behind having an interrupt request on an error. And that enables your system software or firmware to do a soft reset on the controller, a hard reset on the entire system, or a soft reset on everything. So it gives the power back to you. So we'll detect the faults in the controller, and Mixel will do the same thing on the PHY. And that way, that gives you a strong methodology to move forward as you're engaging in this market. So I'm going to turn this back over to Justin for the conclusion here, or the rest of the status.
Okay. I'm just double checking. All right. So now that we've reviewed MIPI PHY and Controller for automotive applications, I thought it'd be good to look at some real life use cases. So this first example here is an example camera system from NXP, which is comprised of two parts. On the left, we have the image sensor subsystem, which includes the sensor itself and supporting circuitry for image capture and for organizing the data for transmission using CSI-2 and a DPHY TX. On the right is the system level SoC, which leverages MIPI DPHY RX Plus, the patented configuration I mentioned earlier from Mixel, which is receiving the image data. The RX PHY also deserializes the data and then transmits the parallel data to the Rambus CSI-2 controller. The data is then sent to the signal processing subassembly, which is part of the NXP IC. Now, both sides in this case required a MIPI DPHY interface using CSI-2, and Mixel provided the DPHY TX and DPHY RX, integrated with the Rambus CSI-2 TX and RX controllers. So another customer use case is the GW5 Automotive Geometric Processor. The GW5 is used for ADAS and other automotive applications, and this is actually the third generation of their automotive geometric processor that is using Mixel's PHY and the Rambus controller. And Geo is using MIPI CSI-2 as the communication link between sensors and the computer vision processor. In the center of the block diagram, we can see the camera vision processor, or CVP, receiving data from the sensor using CSI-2 RX, and then driving the data using MIPI CSI-2 TX to an automotive long-reach SerDes link, which then drives a high-resolution display using a MIPI DSI-based PHY. For computer vision applications, the unprocessed high-resolution data is being transmitted from the CVP to a computer vision processor using a pair of MIPI CSI-2 RX and CSI-2 TX interfaces on MIPI DPHY. So in this example, Mixel provided area-optimized versions of the DPHY TX and RX with the Rambus CSI-2 TX and RX controllers. So this last customer use case actually required an ASIL-B certified MIPI IP. Renesys, previously IDT, was designing an automotive SoC to interface between multiple sensors with parallel channel acquisition and the electronic control unit, or ECU. Huge amounts of data come in parallel to be processed by the Renesys SoC and then sent to the ECU. In order to handle this level of data, Renesys used a DPHY with CSI-2 TX using 4 data lanes at 2.5 gigabits per second per lane, and this supported an aggregate bandwidth of 10 gigabits per second to be sent to the host ECU. The controller used a TX FIFO for bandwidth matching, a feature of the controller that Joe mentioned earlier in the presentation. Since this was a safety-critical application, they needed the MIPI IP to support ACQ100 Auto Grade 1 with junction temperature up to 150 degrees Celsius, and required an ISO 26262 ASIL-B certified IP supported by internal and external safety mechanisms. Mixel provided the MIPI DPHY in this case, and Rambus provided the MIPI CSI-2 controller. So with that just about concludes our presentation. But before we wrap up, I wanted to leave you with some key takeaways as you think about designing automotive sensors for autonomous driving. So MIPI was designed from the ground up for low power applications, and as a result, MIPI CSI-2 has really become the de facto standard for automotive camera and sensors. And cars are requiring increasing number of sensors as automotive automation features progress from level 0 to level 3 and higher. MIPI PHY and MIPI CSI-2 targeted to automotive applications need to support many testability features, such as in-system testing. And by leveraging ASIL-B functional safety deliverables, and or an ASIL B certified IP, automotive SOC designers can target higher ASIL levels for their product, essential for mission critical applications. So thank you for joining our presentation today. And with that, Joe and I can take some questions from the audience. Thanks.
Thank you, Joe and Justin. So we have some really interesting questions. MIPI CSI-2 it's often associated with CMOS camera sensors used for still photography and streaming video. Can you speak to CSI-2 solutions that may be applicable for, say, broader image sensors used in automotive platforms such as lidars and sonars?
As I was mentioning before, the electromagnetic spectrum has a huge impact on the lane rates required. So the higher frequency, generally the higher resolution you're going to get. So in that case, you'll need a really high throughput C or D PHY, a decent process node to be able to close timing on a 3.5 gigasim C PHY, typically 5, 7, 16 nanometer process node. But if you want to go and do, looking at more larger objects, or maybe a backup camera that doesn't need to have such high throughput, you'll use very commonly is a 2.5 or 1 gigabyte, 1.5 gigabyte D PHY, which is is a really relatively off-the-shelf solution that's used all over the place. So that requires a slightly lower clock rate, and that gives you more flexibility in the type of process node you can implement. 40 nanometer is real popular in this space, 28 nanometer, things like that. So those are really standard processes for this market. And the nice thing about this standard is it allows all these things to come in. You can do a low-end camera with some advanced features if you want to, like a special region of interest, even at a lower bandwidth rate. You can do extended virtual channels at either the high end or the low end. So you still have the flexibility of all the features. It's just you're focused on a particular clock rate and lane rate. So it is flexible in that regard. Justin, you have anything to add to that?
I was just going to mention, Grigor's presentation earlier also kind of touched on this, right? The idea of you're starting to see more use of CSI-2, not just in strictly cameras, but different kinds of sensors, and lidar was definitely one that he mentioned that it's not quite picking up yet, but you're starting to see definitely seeing it more.
I agree with that. Yeah, it's definitely becoming more popular.
Yeah, I mean, you have to also keep in mind the product life cycle for these, or development cycle as well. We're talking years, right? So I mean, early in the presentation we mentioned, we're seeing increase in requests for C-PHY, but the three customer use cases we talked about are all D-PHY. Well, that's because how long did it take to get these products into the market and get it qualified, get it approved, right? So that's kind of one thing that we kind of see, right, Joe and I, we see is, because of our role in the MIPI ecosystem, is we do kind of see where the market's kind of going before it gets into the end market. So that's kind of really where,
Yeah, you're right. You're right. That's a good point. There have been C-PHY only. People, come to the door and they say, hey, I just want C-PHY. Can you just not talk to me about D-PHY at all? And that's fine. Yeah, and you're right. It's going to take a while before those products hit the road. Absolutely.
Yeah, thanks, Joe and Justin. The second question is, based on what you see in the ecosystem today, are MIPI CSI-2 IP solutions broadly available on leading process nodes across the foundries?
Yeah, that's a good question. I'll let the lead on the PHY side take that one, Justin.
I mean, you definitely, Joe already alluded to it, right? But we're definitely seeing everything from the most advanced nodes 5 below to things that in kind of the core 16, 28, 40, right? It just really depends on the application and the kind of bandwidth that we're talking about, right? But as Joe said, a lot of the sensors now still can 1.5 gig and 2.5 gig is still sufficient for a lot of the applications we're seeing. But when you start trying to push those speeds, then that's really where you start seeing the need for the more advanced nodes.
Yeah, exactly. And you know, we both do a really good job. Like the controller RTL has no process specific information, so we basically want to know if Mixel can support that process node. And then the next question is, you know, what kind of clock rates do you need, and can that process actually handle it? You know, we can do a quick synthesis and verify that, or enable our clients to do that themselves. Yeah, so that's a really good question.
Can you speak to common CSI-2 subsystem configuration options requested by your customers, Joe and Justin?
Yeah, do you want me to go first, Justin?
Yeah, maybe you go first. I mean,
okay.
you
Yeah,
kind of
so
mentioned,
yeah, so I mean, some of the common configurations for the controller are having, like on the TX side, there's a FIFO for the bandwidth matching. That's something that we do all the time. Most people are doing the packet interface, but every once in a while, you know, people need the video and horizontal sync. So there's a video interface that is available as well, and sometimes, you know, that includes support for virtual channels as well, so you can have a video interface per virtual channel. Not quite clear of what those new architectures are doing with that, but that's something that's been recently deployed. And then I mentioned the bifurcation. So a lot of clients are trying to balance their market requirements by handling, you know, a high and high bandwidth sensor and some lower bandwidth sensors in the same IC. So that's somewhat common as well. So yeah, so the things on your table, you know, the CSI controller table v3.0, that seems to be like one of the golden standards right now. And a lot of people are, you know, really dipping their toes in the 4.0 features. So those are really taking off as well. It's really quite amazing to see some of the new features being adopted more quickly than I have seen on the standard, new standard versions coming out. So I think MIPI org is really hitting the high notes for this market.
Yeah, I would just mention on the PHY side, I mentioned it earlier, but like the TX Plus and RX Plus, right, is a configuration that we created because of a customer request, and for automotive, and really a lot of automotive customers really like having that in-system testability that comes with this configuration, right, without the area penalty of the universal, right, because that's traditionally how you would have to have that extra testability if you want it in system. So yeah, and then as Joe said,
I would imagine just in addition to area, you probably have power thermal constraints as well as you're going through the architecture.
Right. Yeah, and in terms of, like, you know, number of lanes, of course, you do see some people. Depends on where you are in the market, right? But some people are really pushing the top speeds. Also need CFI. We're seeing more requests for top speeds for CFI, right? And really pushing that bandwidth. But yeah, but not in all cases.
So we are reaching the end of our time limit for this presentation. I wanted to thank again Justin and Joe for an incredible presentation on sensor solutions for autonomous driving.
Great.
Thanks, everybody. Good job, everyone.
See you
Bye.
soon.